the top here is our percent yield equation. So this is one of the equations you guys are going to need to remember. It's pretty straightforward, though. The purpose of this is just so that we can understand how much of what we expected to get out of a reaction did we actually get. So it describes that for us. If we use our BCA chart and stoichiometry to get a theoretical yield, and we run the reaction and we get that value, then we would have a percent yield of 100%. We got everything that we expected to get. If we calculate how much we should get as the result of a reaction, and we only get half of that, then our actual yield amount will about half of what our theoretical yield was, and the percent yield would be 50%. Another thing that's important to understand about this equation is because we're doing a number divided by a number and calculating it by a percent, this is not going to have units other than percent. So we can either use and, because these are going to be for the same thing, so it would be sodium chloride and sodium chloride, but because it's the same kind of thing, we can use either grams or moles to calculate percent yield. It doesn't really make a difference because the units cancel out. So as long as we're measuring the same chemical species and we're consistent with using grams for both measurements or moles for both measurements, it doesn't matter as long as we're consistent. So yesterday, we talked a little bit about what this Hoffman apparatus problem was. I'm just going to do another one with you guys and then let you finish these problems. So number 2 says, recall that liquid sodium reacts with chlorine gas to produce sodium chloride. That's just table salt. You want to produce 851 grams of sodium chloride. How many grams of sodium are needed? So it's given us grams in 2 different places here. But keep in mind, when we do stoichiometry and when we do calculations with a BCA chart, we have to do it in moles. The reason for that is because the different chemical elements and different molecules have different atomic masses or different molecular masses. And so we can't really compare the number of grams of sodium to the number of grams of chlorine because their grams per mole are different. And what matters is the ratio of the numbers of molecules and the number of atoms that we have interacting. So we're going to go through our BCA chart and fill in this information as we go along. So it tells us that our reaction is chlorine gas with sodium to produce sodium chloride. So I'm going to just write sodium plus chlorine gas, and chlorine is a diatomic gas. Yields sodium chloride, and this is not balanced. If we've got 2 chlorines in a molecule and we're producing sodium chloride, we're going to produce 2 sodium chloride molecules, and we're also going to need 2 atoms of sodium to be able to produce that. So there's our balanced equation. Then for our BCA chart, I just write BCA down the side there. I like to draw a line there over the A too, just so I kind of know. I think about it as those old problems from elementary school where we're adding things together or subtracting things. That's the way that I think about each of these columns. Next, we're told that we're going to produce 581 grams of sodium chloride. So we're going to start with no moles, but I can't put grams there. I have to convert that value to moles. So in order to do that, I'm going to write 581 grams of sodium chloride, and then I need to know how many grams per mole I have for sodium chloride. So for every mole of sodium chloride, I'm going to have a mass that comes from the periodic table. You guys hopefully remember this from talking about it a couple of months ago. I'm going to add these together. I need the mass for 1 sodium atom and 1 chlorine atom. So I think that my daughter took off with my graphing calculator, so I'm doing this on my phone today until I go downstairs and find it. So I've got 22.99 grams per mole for sodium. And for chlorine, I have 35.453 grams per mole. So I would expect that if I had 1 mole, if I had 6.02 times 10 to the 23rd molecules of sodium chloride, it would have a mass of 58 grams. So I'm going to come over here. Oops, NaI is the wrong one. So the reason these two numbers go together in this conversion factor is because they are equal to each other. 1 mole of sodium chloride equals 58.443 grams of sodium chloride. In order to calculate then how many moles we have, you can kind of look at this and it's going to be about 10. We have 581 divided by 58.443 grams. So I've got, say, 9.9 moles of sodium chloride. This is the number that I'm going to put in my BCA chart. So the amount of change that I'm going to have is I'm going to get 9.9 moles of sodium chloride. Right? So at the end of this reaction, that's how much I'm going to have. What we're being asked is how many grams of sodium we need. How much sodium are we going to use to be able to pull this off? Well, in order to solve for that, I'm going to say, okay, so I've got 9.9 moles of sodium chloride. And for every I need to figure out how many moles I need to produce that much. So I'm going to look at my balanced equation to get a ratio of sodium chloride to sodium. And what I see is that for every 2 parts sodium, I get 2 parts sodium chloride. So to convert that, the thing I would need to cancel out is this moles of sodium chloride. So I'm going to write that first, 2 moles of sodium chloride. And for every 2 moles of sodium chloride that I produce, I'm going to need 2 moles of sodium. You guys can probably recognize that multiplying this times 2 divided by 2 is the same as multiplying by 1. And so this is going to take 9.9 moles of sodium to be able to produce 9.9 moles of sodium chloride. But that's not what the question is asking us. It's asking us for grams of sodium. Oops, just sodium. It's asking us for grams. And so what we're going to need to do is take that 9.9 moles of sodium and use our atomic mass again from the periodic table. The atomic mass for sodium is 22.99. So I need to multiply that times 22.99 grams of sodium for every 1 mole of sodium. So this way, moles of sodium will cancel. Let me go back to my calculator. I still have my value in there. I rounded it when I wrote it down, but I kept it in my calculator. I like to keep them in my calculator as long as I can, just so I don't introduce rounding errors. So now I've got 228.6 grams of sodium. And for those of you who enjoy significant figures, we have 3 sig figs here. We have more than 3 sig figs here. So we could give our answer in 3 significant figures, and that would be okay. So, if you want to round it, 229 grams of sodium is how much we should get. So some of these problems are going to take a couple of steps because you need to convert from moles to grams or from grams to moles. The other thing you're going to notice is you don't have to fill in the entire chart. You can, but you don't have to. Yeah. So what questions do you guys have? Anybody have questions?
Can you show me how you got that 58.443?
Yeah. So the 58.4, where am I going to put that? So let me go so I can see my screen. So to get that 58.443, what we have to do is add our grams per mole for sodium to our chlorine grams per mole. And we only have one of each of those in our product. And so I'm going to look at my periodic table. So here for sodium, I have 22.990. So what that's telling me is that my atomic mass for sodium is 22.990 grams for every mole that we have. And I'm going to add to that the atomic weight for chlorine, for a single chlorine atom, which is 35.453. And that's how many grams 1 mole of chlorine will weigh. how much mass it has. And then we add those together in our calculator. You guys can't see my calculator. 22.99. There's 22.99. Oops. I get 58.443. So what that tells me, if I've got 1 mole of these sodium chloride atoms, that it's going to weigh 58.443 grams. And you could do this with any of these. So down here we've got glucose. Let me just switch colors so look there. So with glucose, we've got 6 carbons, 12 hydrogens, and 6 oxygens. And so when you figure out the atomic mass for glucose, you're going to say, okay, I've got 6 of those times the mass for a single carbon, which is going to be 12.011. For hydrogen, you're going to have 12 of them times the mass of a mole of hydrogen is 1.008. For oxygen, we have 6 of them. So we're going to multiply 6 times the mass of a mole of oxygen atoms, which is 15.999. I like to make these charts for this. So 6 times 12.11. 12 times 1.008. That's not right. And so basically what we have to do is account for the mass of each type, of each element in each atom that shows up in a molecule, so that we can measure them out by weighing them. Dang. This thing is not like registering me very well. And so I got that this has a mass of 180.156 grams for every mole of glucose. And so that's what I'm going to need to use, this relationship, how many grams per mole. That's what I'm going to use to convert my grams of glucose into moles, and then this doesn't ask me to go back into moles from grams for that particular one. Does that help? Yeah.
Yes, thank you.
You're welcome. Okay, Jack says, do we not have to do anything with percent yield? So percent yield. Yeah, so percent yield is stuff that shows up later. So I'm not sure if you guys can see this or not. I just have a box that says you're presenting on my screen. I can't actually see what I'm presenting. So there are problems on the back that asks you to come up with the percent yield for something. So starting with problem number 4, it says suppose you actually recovered this many grams. So what you're going to do is use your BCA chart to figure out how many grams of zinc chloride you should get. And then you're told you actually get a different amount. And you're going to use those two numbers to figure out your percent yield.